I'm Shanshan. I'm a senior engineering director at Uber. At Uber, I lead storage, search, and data platform teams. My team is responsible for Uber's online trip serving stack, as well as offline data analytics workloads across the entire company. Today, I'm excited to share how we are advancing search and observability at Uber with OpenSearch technology. I'm sure many of you use Uber. Raise your hand if you never used Uber before. Nobody? Okay, so Uber is well known for our ride-sharing service. Besides ride-sharing, we also offer Uber Eats or Uber delivery business. Uber Eats is online food delivery service. Customers can order restaurant food, also groceries delivered right next to their doors. For both Uber Rides and Uber Eats, search platform played a very critical role. We use search to do real-time driver and rider matching. Customers use search to find and also browse the menus from their mobile applications. Search is on the critical path for Uber's real-time operations and overall business success. Traditionally, we leverage on lexical search or text search. Slowly, what we realize is lexical search has lots of limitations and cannot always meet our customers' requirements. The search quality of lexical search is not always very good. To show some examples, for example, if you go to our mobile app, input vegan, gluten-free burger, or ideally you want to just search a vegan burger, but the search result may return you something like vegan dessert, gluten-free bread, and also meat-based burgers. Well, in this case, you may be very disappointed. To address this problem, we adopt semantic search technology. Semantic search can understand the intent and also contextual meaning behind the search queries. Semantic search can also deliver the very relevant search result and also eventually improve our search conversion rate to make our Uber's business more successful. So let me dive into a little bit details of our semantic search architecture. Fundamentally, at the core, behind the scenes, semantic search is all about embeddings. So in our use case, we build search index based on the stores and also based on all the items. Based on the input of stores and items, the embedding models was trained. We ingest the embedding models into our storage search systems, that is our search index. When a user comes to our mobile applications, try to find some items, they will input the text into their phone. Based on these user queries, the query embedding is also generated real-time on the fly. We compare these embeddings with all the embeddings in our search systems in our index, then we can come up with better query result. So our architecture is very classic two-phase model. One is called first phase retrieval. Second is called second phase ranking. For the first phase retrieval, we use coarse-grained retrieval model. This model is able to search among all the search index, the billions of items. We were able to narrow down among all these billions of items to a few thousand items. Then in the second phase re-ranking, we apply more fine-grained models. And we compare the similarity by sorting all these thousands of items. Further, we can narrow them down to a few dozens of items, eventually display on the UI. Also, to contiguously improve the search user experience, we have a feedback loop. As you can see from the diagram, based on the LLMs, we further train based on the user input and also based on the user click, the conversion rate, we have a fine-tuned training model. We use this fine-tuned training model, have a feedback loop to our embedding model, then eventually to tune our search index. This feedback loop can help us to have better user experience, more personalized user experience. And also, this personalized user experience can help to improve our search conversion rate over time. So at Uber, our platform supports 7 million earners, 130 million riders, more than 80 million eaters around the world. This large user base creates more than 1 million concurrent transactions at any time, which further translates to a large amount of workloads generated on top of our search and observability platforms. Our search platform handles more than 50 billion search queries a day. This many search queries powers on more than 50 unique search use cases. So in the previous slide, I talked about Uber Eats. Besides Uber Eats, we have many other search use cases. All these search use cases deployed on over 150 clusters. And each cluster has a scale of several hundred, and some of them is even thousands nodes. Our observability platform also have a massive scale. We are handling 5 billion plus metrics per second. Also has a 160 billion cardinality. So with such a large scale, we have a unique challenge of maintaining service reliability and also provide the need to perform, which is very much required by our real-time workloads. For observability, we have been using a homegrown matrix called M3. Many of you probably know it from our engineering blog. Over time, this homegrown matrix system created some limitations, and we saw a lot of shortcomings. For example, it doesn't support high cardinality query. It struggles with the resiliency in the face of a zonal failure. We currently deploy our platform across on-prem as well as the cloud provider data centers. So zone often could fail due to power outage. In an event of a zone failure, we really need metrics to diagnostic, but often it doesn't available, unfortunately. Also, this homegrown matrix system has lots of challenge in terms of operational cost. So as an infrastructure team, we want to reduce the cost to as low as possible, but due to the absence of built-in governance features, we couldn't control our matrix cost, which is quite significant at this moment. To address all these challenges, we are investing in development of a next generation matrix platform, building on top of OpenSearch. One key issue with our homegrown solution is its usage of a M3 query language. You probably never heard of M3 query language, but heard a lot of the Promises query language, because Promises query language is the industry standard, while M3QM is not. So along with this transition, we would like to adopt and support industry standard query language to improve compatibility, also to improve our developer experience. This diagram shows the high-level architecture with a time series database support. As everybody knows, OpenSearch is well known for its support in large-scale logging and tracing use cases. But because it doesn't have a natively built-in time series database, so it couldn't support large-scale metrics use case. We aim to bridge this gap. Our engineers are working on a solution which is inspired by Promise's time series database design. What we want to do is to build a time series engine inside of the OpenSearch server. We also have the time series engine with predicted pushdown. Also, as I mentioned in the previous slide, we also want to align with the industry standard, adopt Promise's query language to support better queries. Our broader goal here is to position OpenSearch as a comprehensive and also competitive solution for all observability use cases, logging, tracing, metrics, all on one single platform, that is OpenSearch. So at Uber, our strategy is to enhance, to embrace industry standard and also to innovate in collaboration with our ecosystem partners. We rely on a wide range of solutions from both open source communities as well as cloud providers. Besides OpenSearch, we also have Cassandra for key value store. We also have Kafka for messaging. We have Flink and Keynote for real-time data processing and data analytics processing. We also have Spark Presto for our batch workload processing. We use Oracle Object Storage for our online trip serving real-time workload handling. We rely on Google Cloud Storage for our data lake, data analytics. We also use cloud database to power on our real-time transactional databases. We actively share our work through Uber engineering blogs. We also actively participate in community conferences. We organize meetups right in our Sunnyvale Uber office, which is only several miles away from this hotel. So we would like to sincerely invite all of you join our meetup. Meet us in our Uber Sunnyvale office. We would like to hear your learnings, your challenges. We would like to tackle all the interesting problems together with all of you. In addition to this keynote, I would like to highlight several talks by our Uber engineers that showcase our contribution to OpenSearch ecosystem. These talks cover our work in shaping a decoupled cloud-native architecture with separate reader and writer roles, a high-throughput messaging protocol for distributed coordination, and a pool-based ingestion model optimized for serverless environment. Developed in close collaboration with the OpenSearch community, these innovations help position OpenSearch 3.0 as a next-generation open source engine built for cloud-native Uber-scale deployment. I would like to make a disclaimer here. So for the Uber search use case, which currently is still running on top of a homegrown search solution called Lucene Plus, we haven't adopted OpenSearch yet. What we hope to do is by filling in all the large-scale gaps identified in OpenSearch technology, we can migrate our Uber delivery business and many more use cases I talked about to be on board on OpenSearch platform going forward. If any of our work, any of our talks are interesting you, be sure to check them out for all the details. We are also actively looking for passionate OpenSearch engineers to join us in pushing the boundaries of semantic search and observability within the OpenSearch ecosystem. Your ideas and contributions could help shape the future of these capabilities in ways we only began to imagine. With that, I concluded my talk, and thanks everyone.